We've spent a lot of time talking about different conversions tests, so now we want to focus on how to tell what conversions test we should use, and how to deal with problems that require more than one type of conversions test. So here, for example, we have a k factorial over a k to the kth plus 19. Normally, for something that just involved these two terms, we would use a ratio test because the k factorial is pointing us in that direction. However, in this case, we have a plus 19 in the denominator. So if we try and use the ratio test, we will end up with an extra term that doesn't simplify when we turn it into fraction. The same thing would happen if we tried to use the root test instead. If we use the root test, we would run into exactly the same problem that when we try and take the kth root of anything over k to the k plus 19, we can't distribute this kth root to a binomial, only to a monomial. So we can't use the root test directly on this as well. So that leaves us with a comparison test, because if we use a comparison test, we might be able to remove the term that's giving us a hard time here. So going over to the comparison test, there we go, really slow scrolling. The comparison test, so we have two summations, one that is given and one that we have to think up. So let the summation of a sub k and the summation of b sub k be series with positive terms. If 0 is less than a sub k is less than or equal to b sub k, so this guy is small, and b sub k converges, so this goes to some finite number. Let's just throw one out. So let's say like 3. Then a sub k converges, and let's talk about why. So if this goes to 3 and it is greater than a sub k, then a sub k can't go past 3. So it's limited. It must stay less than or equal to 3. Looking at the other if statement, if 0 is less than b sub k is less than or equal to a sub k, and b sub k diverges, in other words, b sub k goes to infinity, if this one is greater than it, there's no way it can go to some finite number. It can't go to 3 or 4. It has to also go to infinity. So if this is true, and the summation of b sub k diverges, then it's written wrong. There should be an a. Then a sub k also diverges. So the comparison test we're going to use allows us to get rid of the 19 in the denominator. So we'll use the comparison test because the extra term in the denominator will prevent us from using the root or ratio test directly. So our original a sub k is equal to k factorial over k to the k plus 19. We're going to compare it to the exact same equation, but without, or statement, but without the 19. So now this will be our b sub k, and we have to decide, is this greater than or less than? So if we have a denominator with extra in it, so for example 1/3 compared to 1/2, 1/3 has more in the denominator, and so that fraction ends up being less. So by the same logic, this should be less as well, just like 1/2 plus 19 is definitely less than just 1/2. So then we're making an argument that a sub k is less than b sub k. We want to make sure that b sub k converges. So this needs to converge. If it diverges, the test would be inconclusive, because all it would be showing is that something larger went to infinity, which doesn't tell us anything about the smaller thing. It could be finite, but it also could go to infinity. There's no requirement. But if we manage to show that this converges, then the summation that is smaller than it must also converge, or the summation that's made up of terms that are smaller. So now we just have to figure out whether or not this one converges or diverges. So does the summation k equals 1 to infinity of k factorial over k to the k diverge or converge. So now that we don't have the 19 in the denominator, we can go back to the root test. And looking at the root test over here, we're going to take the limit as k goes to infinity of a sub k, the ratio test. I keep saying root, but I mean ratio, plus 1 over a sub k. If r ends up being less than 1, then the entire series will converge. If r is greater than 1, the series diverges. And if r is equal to 1, then we have an inconclusive result. It's unknown whether or not the series would converge or diverge. Okay, so in this case, we need to add a plus 1 to all of our terms and then stack it over the exact same a sub k in the denominator. So r is equal to the limit as k goes to infinity of k plus 1 factorial over k plus 1 to the k plus 1. And all of that gets stacked over the original k plus 1, k to the k. All right, so let's go over here and move this fraction, and we'll do some scratch work. We need to reduce the fraction k plus 1 factorial over k plus 1 to the k plus 1. And that whole thing is written over the exact same thing that we originally given, but in the denominator. So we'll just skip our writing it in the denominator and flip it over. So we have k to the k over k factorial. So if we start reducing this, we have the factorial canceling with this entire k, and we have our k plus 1, which we can rewrite as k plus 1 to the k times k plus 1. That will give us the two terms k and the plus 1. If we put these terms together and added them up, we get back to where we were. And that will cancel with this, which leaves us with k to the k over k plus 1 to the k. And just because we went past this real quickly, let's recall what a factorial is. K plus 1 factorial is the same thing as k plus 1 times k minus 1, all the way down to 2, and then 1. So if we write out these terms for k factorial, we get essentially the same thing. K times k minus 1 times k minus 2, all the way down to 2 and to 1. So all of these terms would cancel, leaving us only with the k plus 1. That means our fraction can be reduced to just k to the k over k plus 1 to the k. Coming back over here, we have the limit as k goes to infinity of k to the k over k plus 1 to the k. This can be rewritten as just the limit as k goes to infinity of k over k plus 1 all to the k. And we can use our trick to try and simplify this fraction so that we can deal with the limit a little easier, because at this point we would have the numerator, the denominator, and the power all going to infinity. So if we use a rewrite trick and multiply the interior fraction by 1 over k over 1 over k to the k, this will simplify. These two k's will cancel, giving us a 1. These two k's will cancel, giving us a 1. And we'll be left with 1 over k here. So that leaves us with the limit as k goes to infinity of 1 over 1 plus 1 over k, all to the k. Now as k goes to infinity, this fraction will go towards 0, and that will leave us with 1 and 1. So this will give us a setup of 1 to infinity, which means that we'll need to use the limit as k goes to infinity of e to the ln of our original a sub k. This is a trick that we went over when we talked about L'Hopital's rule when it was first introduced. We're going to apply it in this problem. When using this trick, we essentially will ignore the e until the very end of the limit, and at what point we will write the limit over e instead, or to the power of e, in the power of e. There we go, I said it correctly. So when we find our limit, we'll write it as the power of e. So this implies that we have the limit as k goes to infinity of the ln of 1 over 1 plus 1 over k to the k. Using the laws of logs, I can move this out. So that allows me to write the limit as k goes to infinity, k ln of 1 over 1 plus 1 over k. Now this problem will be giving us, as k goes to infinity, k will go to infinity, and as k goes to infinity, this part of this fraction down here will go to 0, so I'll end up with ln of 1 and ln of 1 of 0, so I have a 0 times infinity problem, which doesn't fit L'Hopital's rule, but I can use a rewrite trick and recall that 1 over k is exactly the same as k, because using my keep change flip, I multiply the numerator times the denominator reciprocaled, so that's just k. So rewriting here, I have the limit as k goes to infinity of ln of 1 over 1 plus 1 over k, all over 1 over k. Now I have the numerator still going to 0 and the denominator now going to 0. A 0 over 0 case will allow me to use L'Hopital's. So I need to take the derivative of the numerator and the derivative of the denominator. The derivative of the denominator isn't too bad, it's 1 over k, so rewriting that as k to the negative 1, I move the power out in front. That gives me negative 1 times k, subtracting 1 from the power to the negative 2, and rewriting I have negative 1 over k squared. That's the derivative of the bottom. The derivative of the numerator has chain rule twice, and that second chain rule is a little hidden. So the normal derivative of ln of x is just 1 over x. So using that, we have the derivative of ln of 1 over 1 plus 1 over k. That gives us 1 over 1 over 1 over 1 plus over k. That's a crazy fraction, but that's what it gets us. This x has been replaced with this entire fraction. And so this entire fraction is going into the denominator. We also have to take the derivative of the inside. So rewriting the derivative of the inside separately, I need to take the derivative of 1 over 1 plus 1 over k. Okay, and that is the same thing as 1 plus 1 over k to the negative 1. And so here's our second set of chain rule. Otherwise, we'd have to use the quotient rule on this. So moving the exponent out in front, I have negative 1 times the original, 1 over k. Subtracting 1, I have negative 2. And then taking the derivative of the inside, well, that's the same as the derivative we took before. So that's just 1 over k squared with a negative in front. So our derivatives are here, and this times this for the second derivative, which required 2 different chain rules. So rewriting, we have the denominator is just, and rewriting our limit as well. Limit k goes to infinity scrolling back to where I was, I have the denominator is just negative 1 over negative k squared. And then I have my chain rule, which was 1 over 1 over 1 plus 1 over k. And if I just flip that, I just get 1 plus 1 over k. So I have 1 plus 1 over k times negative 1 plus 1 over k to the negative 2 times negative 1 over k squared for the derivative of the numerator. So this is to the negative 2, this is a 1, so those two will come together to just give me a negative 1 as the exponent. So I have 1 plus 1 over k to the negative 1. I have a negative here, and this entire inside derivative will cancel with this denominator. So the only thing I have left is the limit as k goes to infinity of 1 plus 1 over k to the negative 1 with a negative in front. Now as this goes to infinity, this second fraction will go to 0 again, and I get just 1 to the negative 1, which is still just 1, and a negative in front, so the whole limit goes to negative 1. And then recall that we use the limit as k goes to infinity of e to the ln of a sub k to get here. So I need to write the actual final limit So the original limit, the r limit, is equal to e to the negative 1, which is better known as 1 over e, which is less than 1. So we have that the summation k factorial over k to the k going from 1 to infinity, converges. Because this converges, and we showed that it is greater than the original, our original problem also converges. So we can go back up to the beginning and say this converges by the comparison test. Okay, let me just zoom out a bit so we can see more of this all written together. We had to take a very complicated limit to show that our b sub k converges. That's what all this work down here was. But the big idea was to find a similar problem to what we were given that eliminates the extra term that made it so difficult to use a ratio or root test. All right, if you have any questions on this video, reach out to me through the Hey Professor discussion board or through Pronto, or send me an email, and I will talk to you guys soon.